One of the most important tools for studying Lipschitz functions is the Arzela Ascoli theorem, which gives conditions for when we can take a sequence of Lipschitz functions and pass to a convergent subsequence. So a version of Arzela Ascoli goes as follows. So suppose that we have two metric spaces x and y, where x is separable, and we have a sequence of uniformly L Lipschitz functions from x into y. And we also assume that if we fix any point x in the metric space big X, then f sub k of x, or the sequence f sub k of x, has compact closure in the metric space y. Then there is a subsequence that converges uniformly on compact sets. That is to say, if we fix any compact set in X, the subsequence will converge uniformly to a Lipschitz function on that set. So throughout this course, we'll be using the special case of this theorem, that if we have a sequence of Lipschitz functions from one Euclidean space into another, and these Lipschitz functions are uniformly bounded on every compact set. So that is to say, for any fixed compact set, the sequence of functions, when restricted to the set, form a bounded family, even though the bound can change between different compact sets. Then there is a subsequence that converges uniformly on compact subsets of Euclidean space. The Arzela Ascoli theorem is used often in a style of argument called a compactness argument. So in order to convey what kind of argument this is, we're going to just review a very simple example from undergraduate analysis. So recall that if you have a continuous function on the unit interval into the reals, then it's bounded. So recall how this proof went. So our goal is to show that the function f of x is at most some number n for all x in the interval. So what we do is we assume instead that the contrary is false, that this function is not bounded on the interval. So that implies that for any integer j, we can find an element xj of the unit interval for which f of xj is bigger than j. Now, since the unit interval is compact, this implies that we can pass to a subsequence so that x and j converges to a number x in the unit interval. Now, since f is continuous, f of xjk converges, and thus it's bounded. But this is a contradiction because f of xjk should also be going to infinity because of this lower bound right here. And thus we get a contradiction. So this style of argument where we try to prove a bound by instead assuming that the bound is false and then obtaining a sequence of objects that violate the bound worse and worse, and then passing to a subsequence to get a contradiction, this style of argument is called a compactness argument. So we'll give an explicit example that's going to be relevant to us later when we study the bi-Lip theorem. So for a Lipschitz function f and a cube in Euclidean space, we're going to find the following quantity, omega f of q. So this quantity, so you take the averages over q of the difference between f of y minus an affine map ay over r, and you take an L2 average of this difference, and then you infimize this quantity over all affine maps A. Okay? So this measures how much f looks like an affine map. Okay, so we're going to need this lemma later. So for any delta, we may find an epsilon so that the following holds. So suppose we have a cube in Euclidean space and a Lipschitz function, a one Lipschitz function f from Rm into another Euclidean space. And we suppose that the image of f under the cube is at least delta times the Hausdorff content of the image of the cube is at least delta times the Hausdorff content of the original cube. And we also assume that there exist points x in q and y in 10q that are separated by at least L of q apart, so that f of x minus f of y brings these points close together. So the f of x minus f of y is at most delta over 2x minus y. Then this implies the omega number of 10q must be at least epsilon. So the idea behind the proof is that if f were an affine map, it would be impossible for this estimate to hold and also for this event to hold for some pair of points x and y in 10q that are L of q separated apart. Okay, so because it's impossible for an affine map, that means that it's impossible for there to be a Lipschitz function satisfying similar bounds that is approximately an affine map. So thus, since omega f measures how approximately you are to an affine map, that implies that this omega number has to be large. It has to be at least some number epsilon. So let's take a look at the proof. So without loss generality, by subtracting a constant or a vector from the function f, we can assume that the function is equal to 0 at xq. So instead, we'll assume that the lemma is false. So what this means is that we can find a sequence of one Lipschitz functions fj and points xj in q and yj in 10q so that the following hold. So first, that all the fj are equal to 0 at the center of the cube. The Hausdorff contents of the image of q are at least delta times the Hausdorff content of q. Thirdly, that the points xj and yj are at least L of q apart. Fourthly, the image of xj and yj under the function fj are no more than delta over 2 L of q apart. And finally, that the omega numbers of the functions in 10q are less than 1 over j. So recall that the lemma originally stated that if 1 through 4 are true for some one Lipschitz function and points x and y, that implies that the omega number in 10q has to be at least epsilon. So for the statement to be false, that means that we can find Lipschitz functions satisfying conditions 1 through 4, but omega can be as small as we wish. So we take a sequence of functions so that the omega number is less than 1 over j. Okay, so notice that these functions fj are uniformly bounded on compact sets. So why is this? So let's let m be a number, and we look at the dilate mq, and we're going to look at a point x in mq. If we look at the absolute value of fj of x, this is the same thing as fj of x minus fj of xq, because fj of xq is 0. Since this is one Lipschitz, this is at most x minus xq. And since both are in the cube mq, this is at most m times the diameter of q. And thus, we see that the functions fj are uniformly bounded on the dilate mq. And since any compact set can be contained in such a dilate, that means that the functions are uniformly bounded on compact sets. Okay, so that means that we can apply Arzela Ascoli. So Arzela Ascoli implies that we can find a subsequence of functions that converge uniformly on compact sets to another one Lipschitz function f. And we can also pass to a further subsequence so that xj converges to some number x in q and yj converges some vector y in 10q. Now, because the fj's are converging uniformly and the xj's and yj's are converging, that implies that each one of these statements turns into a corresponding statement for the limiting function. So for example, since the fj's are all equal to 0 at xq, so will f at xq. Now recall that in the week on Hausdorff measures, we had an exercise that said that if you have a sequence of sets converging to another set in Hausdorff distance, then the Hausdorff content of the limiting set is at least the lim sup of the Hausdorff contents of the sets in the limit. So that means that Hausdorff content of f of q is at least the lim sup of the Hausdorff contents of the fjq's, and that's at least delta times the content of q. So that proves B. Similarly, because the xj's and yj's converge, 3 implies C. And similarly, we have that 4 implies D. And finally, because the fj's are converging uniformly on compact sets, they converge uniformly on 10q. So it can be shown that the omega numbers of fj converge to the omega number of f on 10q. And because they're all less than 1 over j, they converge to 0. Okay. But notice that if omega of f in 10q is equal to 0, that implies that f is equal to an affine map in 10q. Okay, so notice what that tells us then. So recall that by B, we have that delta times the content of Q is at least the Hausdorff content of FQ. All right, this is equal to, so F is equal to an affine map on this cube. And recall from our discussion about singular value decompositions that the Hausdorff m-dimensional measure of AQ will equal the product of the singular values times the Hausdorff measure of Q. Now, here we're dealing with Hausdorff contents, but remember that if we're working in an m-dimensional plane, then the Hausdorff m-dimensional content is actually equal to the m-dimensional Hausdorff measure. Now, because the function f is one Lipschitz, that implies that the singular values are all at most 1. So that means that we can trivially bound this above by just lambda m, the smallest singular value, times the Hausdorff content of Q. Now, also recall that a affine map, the lower Lipschitz constant is lambda m. Okay, so this sequence of estimates, if we cancel out the HMQs from each side, we get that lambda m is at least delta. So what this tells us is that the affine map is lower delta Lipschitz, or in other words, it can't shrink the distance between points no more than a factor delta. So thus we have that delta. So thus we have delta times x minus y is no more than lambda m times x minus y. And since that is the lower Lipschitz constant for A, that implies that this is at most a of x minus a of y. Now this equals f on the cube 10q, but by assumption d, this difference is no more than delta over 2 times x minus y. But then we get a contradiction because now this implies delta over 2 is bigger than delta. So we will be using this lemma in the proof of the, so this completes the proof of the lemma. So later on, we'll use this in the proof of the lip by lip theorem.